So we're going to continue learning about alcohols. When we oxidize alcohols, we can actually form an aldehyde or carboxylic acid, depending on the conditions. You don't have to know that a tertiary alcohol gives aldehyde or carboxylic acid. I just want you to know that if we oxidize an alcohol, we can result in a carboxylic acid or an aldehyde. And here is an example. We have one octanol and we oxidize it with potassium dichromate and sulfuric acid, and we get octanol, which is an aldehyde. We can further oxidize it to become a carboxylic acid. So you can't go straight from an alcohol to a carboxylic acid. You have to do a two-step process. You can go from an alcohol to an aldehyde to a carboxylic acid. I do want you to know that. So let's talk about ethers now. And ethers are polar compounds. They have oxygen that has a partial negative charge, and each carbon bonded to it then would have a partial positive charge. So example here is your oxygen right here. You have a carbon here and you have a carbon here. This is a simple carbon diethyl ether. So here you have your unpaired electrons here. So you have your negative dipole there. And here you would have your positive dipole over your carbons. So so you do have a polar molecule. Ethers are polar. Even though it's polar, it doesn't hydrogen bond. Remember, to hydrogen bond, you have to have oxygen and either fluorine, nitrogen, or hydrogen in order for hydrogen bonding to occur. This oxygen isn't bonded to a hydrogen, so it is not going to hydrogen bond because these hydrogens here aren't polar. So you don't have that capability. So you're only going to have those London dispersion forces. Ethers have low boiling points as a result because alcohols here have the ability to hydrogen bond. Ethers do not because there are no polar hydrogens there. Ethers resemble hydrocarbons in their resistance to chemical reaction. They don't react with oxidizing agents like potassium dichromate. They don't react with reducing agents like hydrogen. They're not affected by most acids or bases at moderate temperatures. So they're basically inert. Inert means they're not reactive. So because they don't react, they make good solvents. And they're excellent solvents for organic reactions. Now, one thing ethers were used for back in the day was anesthesia because they actually knock you out. Um, I was I was in high school whenever we used ether to take fruit fly samples in biology class. We collect some, we put them in ether, and it was for fruit fly, it's enough to kill them. And I was supposed to look at them underneath the microscope, look at their wing shape, look at their eyes to determine genetics. We were doing a genetic study. And my lab partner did not close the bottle of ether after we used it on the fruit flies, and I ended up passing out as a result. So yes, be careful with chemicals, especially those that would knock you out upon using them. So amines are classified as primary, secondary, or tertiary, just like alcohols. Amines are also primary, secondary, or tertiary. And that just depends on the number of carbon groups bonded to nitrogen. Here, for example, if there's one carbon group bonded to a nitrogen, it's a primary. If there are two carbon groups, it's secondary. If there are three carbon groups, it's tertiary, just like the alcohols. Now, aliphatic amines, all carbons bonded to nitrogen, are derived from alkyl groups. So alkyl groups, but an aromatic amine, you have one or more bonded to an aryl group. So your nitrogen is bonded to one or more aryl groups for an aromatic amine. And an aryl group looks just like this. It's this honeycomb-looking hexagon. Now, they're called aromatics for a reason. These substances have very specific aromas. And so that's why you have it called aromatic groups. So heterocyclic amines are amines where the nitrogen atom is part of a ring, right here. Here are heterocyclic amines. But if you have a heterocyclic aliphatic amine, you've got those double bonds there, and the nitrogen is part of the ring. This is a heterocyclic aromatic amine. You've got those double bonds, or those double bonds involved. A heterocyclic aliphatic amine, no double bonds, it's completely saturated, but the aromatics have those double bonds as part of it. They don't always have to be the hexagonal shape. It could even be like purine here. And these aromatics, I'm telling you, they are very strong in smells. Most ammonia particles have very strong smell. Most amines have very strong smells. Now, here we have low molecular weight amines. They have sharp penetrating odors. Smelling salts used to be a thing, and if you ever find smelling salts, a lot of them have amines in them. So trimethylamine, if you smell rotting fish, you're smelling trimethylamine. It is very pungent. You also have putrescine, which is butane-diamine, 1,4-butane-diamine, and 1,5-pentadiamine is cadaverine. So the smell of dead bodies, basically, is the cadaverine smell, and putrescine, you can only imagine how wonderful it smells with the name like putrescine. So let's look at the structure of amines. Now, both primary and secondary amines have the nitrogen-hydrogen bond, which means they can form hydrogen bonds with one another. The tertiary amines don't have a nitrogen-hydrogen bond because they're bonded to 3 different carbons. So they can't hydrogen bond with one another. So their melting points and boiling points are going to be much lower in the primary and secondary amines. Now, a nitrogen-hydrogen-nitrogen-hydrogen bond is much weaker than this oxygen hydrogen to another oxygen hydrogen bond. And that's because of the difference in electronegativity. Oxygen is more electronegative than nitrogen, so it's not going to be, so nitrogen isn't going to have as strong a hydrogen bond because the polarity is not as great as the polarity here in the oxygen and hydrogen bond. And you can see that effect here. So here we have three different molecules. They all have approximately the same weight, but you can see how much stronger oxygen hydrogen bonding is than nitrogen hydrogen bonding. Even the weaker nitrogen hydrogen bonding that occurs is still much stronger than the London dispersion forces of no hydrogen bonding. Now, all classes of amines form hydrogen bonds with water, and they're more soluble in water than hydrocarbons of comparable molecular weight because of that ability to hydrogen bond. Now, most low molecular weight amines are completely soluble in water, and higher molecular weight amines, because they have more carbon chains. So instead of being short like this, so like you have CH3 and then you can have like a hydrogen and a hydrogen there, for example. If you have this versus like CH3, CH, or CH3, CH3, and H here, for example, this would be less soluble in water than this molecule because it has more carbon. So the longer the carbon chain, the less soluble in water the molecule is. Now, in our bodies, neurotransmitters and amino acids are comprised of amines. That brief chart I showed you last week with basically the purpose of each one or uses of each functional group showed that amines are part of amino acids and neurotransmitters, which are extremely important in our bodies. So let's look at the basicity of amines. So if we look at the basicity of amines, we see that we can determine which form of the amine exists in body fluids like our blood. So if we're looking at different neurotransmitters or amino acids, we can look and say, well, I know that it's basic because of, we have the NH3, NH2 group. If it is going to be dissolved in our blood that has a pH of 7.4, which is slightly basic, it's going to be in its conjugate acid form with an extra proton. So dopamine, if dopamine's in our blood, it doesn't exist like this. It'll exist like this. So it'll have an extra proton. Now, the most important chemical property of amines is their basicity. So they will react with strong acids to form water-soluble salts. So any amine in our blood will react with strong acids to form water-soluble salts. So norepinephrine is an amine, and in our blood, it becomes a water-soluble salt. Now, the functional group of an aldehyde, we're switching gears here. aldehydes is this carbonyl group right here. In methanol, which is this structure here, it's the simplest aldehyde. And this is the only aldehyde that has the carbonyl group bonded to two hydrogens. Every other one, it's bonded to at least one other carbon. Ethanol, it's only bonded to one other carbon, but any aldehyde larger than ethanol it's got more carbons bonded to it. So it'll have a chain of carbons over here, and you end with this hydrogen and this oxygen here. Now, the functional group of a ketone just has the carbonyl group, the carbon double bonded to an oxygen. Every aldehyde will have this, the carbon double bonded to a hydrogen and also bonded to, or double bonded to an oxygen and also bonded to a hydrogen. A ketone you can identify by looking for this carbonyl group, and it'll have two carbons on either side. Now, that carbonyl bond right here is polar. Oxygen has a negative, and carbon has the positive. So aldehydes and ketones both are polar molecules. Now, it's still not going to, even though it's polar, it's not going to hydrogen bond. But there is something that it can do. So in liquid aldehydes and ketones, you have those weak molecular attractions between that partial positive and that partial negative. No hydrogen bonding is possible. So they still have lower boiling points in alcohols and carboxylic acids, but because they're slightly polar, you do have a little bit more stronger connection. So they're going to have higher melting points and boiling points than alkenes and alkynes and alkanes of similar molecular weight. We're going to stop there, and I'll see you next time.